before doing so. Last time we discussed what? Numerical data. Yes, this. Numerical data to related groups and to independent groups. Let us make a short summary of that. Any questions? Do you have any questions before starting? We discussed numerical data. If you have a numerical outcome variable, numerical outcome, then numerical outcome. And do the one simple t-test or two related samples. Or two independent samples. Independent samples. What was the non-parametric alternative? These are the parametric tests. Parametric. What were the non-parametric alternatives?
Sign t-test.
Sign test. Then
Wilcoxon.
So if it is related, Wilcoxon.
Volist.
And if you have two independent samples, t-test.
Man with
Knee. And we discussed about the assumptions of parametric tests. The parametric tests always have some assumptions. What were the assumptions for the two related and two independent samples t-test? Assumptions. Assumptions means the conditions you have to meet in order to conduct this test, this parametric test. If you cannot meet the assumptions, then you go for the non-parametric alternative. What were the assumptions for the two independent samples?
Normal distribution.
Normal distributions, one. Second?
Sample size.
Yeah, sample size, enough sample size. And for the two independent samples t-test or the student t-test, we call it also. Student t-test. We had another, a third one.
Homogeneity of variables.
Sorry, again, Jana?
Homogeneity of variables.
Thank
or
you.
something like
Homogeneity of the variances. Or equality of the variances. Homogeneity of variances. Do you remember the test for homogeneity of variances?
Independent t-test.
No, how we check the homogeneity of the variances? Are the variances homogeneous or not? There was a test in SPSS which was doing this for us. If I perform analyze, compare means the independent samples t-test, which we also call the student's t-test, and I want to compare something, a numerical variable between males and females. For example, weight. If I want to compare this, I have this output here. By looking to the output, can you tell me what was the test checking the assumptions of equality of variances?
Levene's test, is it?
Thank you, Levene's test, yes. So this we check with the Levene test. Yes. That's pretty old. That's pretty old. And these parametric tests, they use the mean and standard deviations to calculate the test statistics, while the non-parametric tests, they use what?
They use median and
Thank you. They use the median or the rank. Okay. Now today, that's enough, I think. If you know this much, you know enough. You know more than me. Discard. Okay. Now today, we will discuss numerical data more than 2 independent groups, which is the which test? If you have more than 2 independent groups.
One way ANOVA?
Yes, that was the ANOVA. If you have more than 2 groups, then you do the ANOVA. And we will, in this next second session, we will go over to the categorical data, analysis of the categorical data. Let us look at our book. Numerical data, more than 2 groups. Okay, we have samples from a number of independent groups. A number of means more than 2. More than 2. We have a single numerical. It has to be a numerical outcome, or it can be also ordinal variable. Ordinal variable. You know, I told you, I hope I told you, ordinal variables sometimes can be treated as numerical. Do you remember? Do you remember that? Just let's go to the really basics of our class. When we said data, we had numerical and categorical, right? For numerical data, we further categorize into
continuous, discrete and continuous.
Yes, thank you. Discrete, and continuous. Okay. And categorical data also.
Nominal.
Sometimes nominal.
And ordinal.
Thank you, ordinal. So the examples for these were ordinal data, such as what?
True, false.
Yes, such as nominal, true, false. True.
Education false. Level.
Educational level, for example. Educational level. Or satisfaction, we said. Satisfaction. How can be satisfaction categorized? Satisfaction can be low, for example, medium, or high, right? Now, if you nominal, another example for nominal might be sex. These are the classical examples, male and female. So, how we code all this? If you have a numerical data, okay, it is a scale. It is just something you measure. Something you measure. For example, the blood pressure. Blood pressure. It is 140 historical blood pressure, 145 or something. You have weight. It is 70 kilogram, 72 kilogram millimeter mercury. if your variable is nominal and you have sex, you code it as numbers. For example, you may code male 1 and female 2, but you are free. If you want, instead of male 1, female 2, you may go and code male 2, female 1. Both is okay. If you have an ordinal data, such as satisfaction, and you start coding low as 1, then medium would be 2. And high must be 3 in this case. You see, there is an order. Or you could start from 0, then you have 1 and 2, of course. So, since you have an order here, at the end, when you are going to analyze, when you are going to report your data, the numerical data has to be presented as mean and standard deviations. Or if you have skewed data, you may present it as median and range, minimum, maximum. If you have a categorical data, such as sex, what do you present? You give the n
and percentage.
And percentage. Also for the ordinal data, you are expected to give the n and the percentage here. N, how many of the participants, n and percentage. How many of the participants have selected, have responded low, how many responded medium, how many responded high. For educational level, how many are have a low educational level or primary school, secondary school, high school, etc. You give the n and percentage. But for the ordinal data, if the distances between the categories are considered to be equal, then it is possible to give the mean and standard deviation. Wow. So this is an exception, you see.
I'm sorry, Mr. Could you repeat? I didn't get.
Yeah, that's very important. It's better I repeat it. It's better I repeat it. So for categorical data, normally categorical data, the rule of thumb. The rule is you always present categorical data as n and percentage. Okay? This is the correct answer. If somebody asks you how do you report categorical data, then you say n and percentage. You cannot take the mean of sex. 1 male, 2 female, and the mean is 1.5. No, that wouldn't go. But if you have a categorical ordinal data, such as satisfaction, and you scored it in an order 1, 2, 3, 4, 5, 6, 7, like pain, for example. How much pain do you have? Score it from 0 to 7, 0 to 10, 1 to 10. Then it is possible to treat it as it is not numerical. It is not numerical. It is a categorical ordinal data. But you take the mean, you take its mean, you present its mean as it is numerical data. So here, that's what the book here mentions here. The problem is you have a numerical data or ordinal variable. Both, it goes for both. The ANOVA is for the numerical data. Since the book mentions, I try to explain why we can do an ANOVA for categorical data. Ordinal variable is a categorical variable. Normally, as a rule, we have the one way ANOVA for numerical variables. Okay, and you are interested whether the average, we mean the mean, the mean value of the variables varies in the different groups. in the more than 2 groups. Whether the average platelet count varies in groups of women with different ethnic backgrounds, for example. In my data set here, I have weight, height, which are the other numerical variables, age. These are my numerical variables here, number of children. Okay, so let us assume I want to compare the height between the different educational categories. Okay. Education has more than how many? 1, 2, 3, 4, 5 categories. And I want to see the height. Is the height increasing by education? This is a not a logical hypothesis, sorry for that. But I want to check it. I want to check whether height is different between the education categories. So the test I have to conduct is the one-way ANOVA. You see, you are not familiar. I hope you are familiar with the SPSS. In the SPSS, the parametric tests are under the menu analyze, compare means. And here it's the one-way ANOVA. Okay, I want to see the difference in the height or between the educational groups. Where is education? Mistake. The height education. Here's education. I want to see the mean difference in the height between the educational categories. Let us select here the descriptives and homogeneity of variances. Okay. Here I have my descriptive output. The categories of educational levels, no education, primary school, intermediate school, secondary school, university, and above. Okay, this may be different categories for different countries. We did this in Saudi Arabia. So Saudis have this kind of educational categories. And the mean, let us look to the mean height in centimeters. 155, the illiterate and no educated people. These are 208 people. The majority of the participants are non-educated. Have a height of 155. In primary school, 163, 164, 165. The university, the mean is 165. Any comments? I just open a parenthesis here. I just open the brackets here. Why do you think, you see, the height is increasing? Isn't that interesting? As the education goes on, the height is increasing. Okuduğunda boyun mu uzadı? Is the education increasing the height or what? I need your comments.
Because primary school boys are like shorter, and university like boys are, I mean adult, they are higher.
They're high. So primary school, these are graduates, my dear. These are all adults. The age, let us look at the age. You see, if I sort the age here, sort the age, ascending, okay. The minimum age is 22.
Then I don't have any.
Yeah, you should have. If you think, you will find it. Maximum is 99, you see. So, any other comments? Why we have lower height in those who have a low education?
Is it because of the outliers or?
Yeah, there are maybe some outliers, but
Outliers?
I assume there is another reason. I would love to give you extra scores if you can answer this question. Hmm. Maybe that there is another factor, something else affecting hate. Other than
Be the age, like
yes,
the more
thank you.
the age, the lower the height.
Congratulations. Yes, who was speaking? This gentleman. Yes, thank you. This is exactly this we call the compounding variable. This is about biostatistics. You see, biostatistics answers only your hypothesis, but you as a scientist have to give the computer the mathematics correct hypothesis. If you ask the wrong hypothesis, you will have a wrong answer and you will not know what to do with this answer. Yeah, is the example. I asked the hypothesis: is there a difference between education levels concerning the mean hate? And he says, yes, there is. Hmm? Is there a significant difference? The ANOVA p-value is here, 0.00 something, less than 0.005. So I have to say, I have to accept that there is a significant difference between the groups here. But if they are different, how I'm going to interpret it? That's another question. Therefore, I have to be very careful when formulating my hypothesis. I have to make reasonable, logical hypothesis. Here, it is obvious that those who don't have an education, they are most probably older people. Older people, in the past, it was not possible to have education, so they didn't go to the school. And they are old. Older people, they get shrunk. Their hate is shrinking and getting smaller. See? Okay, that's interesting, isn't it? So, yes, let's go to the book, back to the book. Okay. So, you check for the mean difference between the more than two groups, and there are of course the assumptions, and there are always for the parametric tests almost similar assumptions. In the population of interest, be aware this says the population, the variable is normally distributed. Then the variance in each group is the same. The variance has to be same, and we need a reasonable sample size. Three assumptions. So, is it normal distributed? We have to go and check. How do we check whether this hate is normally distributed between the groups? We can do the which test, which graphs are used to see whether our data is normally distributed or not.
Histogram.
Thank you, histograms. Yes. So I want to compare weight, educational levels, and see whether my data is normally distributing. Histograms. Let us draw an histogram of boy of 8. An histogram of 8. Display normal curve, apply, click OK. I should have now 4 or 5 histograms here. Okay. A histogram for illiterate. Yeah. Is it symmetrical? I would say yes. Histogram for intermediate school and histogram secondary school and university and above. So if if you have a reasonable sample size, let's say the sample size is 18, it is not high. You have to be careful. But if you have a reasonable sample size, your distribution will be symmetrical. Don't worry about the distribution. Okay. So let us assume that we met the first assumption. The data is normally distributed. The second assumption was the differences between the variances. Standard deviation was the square root of variance. Yeah. So when we look at the standard deviation, we look at the variances. Are the variances different here? The variances in the first group is 8.3, then 8.1, 7.6, 8.5, 7.9. What do you think? Do they look different?
Not so much.
We have not so much. We have the Levene test for this, and the Levene statistics says what? Is there a significant, this is the p-value, by the way, significance. Is there a significant difference between the groups?
No.
If it's
No.
more than 0.05, no.
Thank you, you agreed. If it is more than 0.05, it means there is no significant difference. So we met the assumption, we meet the assumption, and we can continue to see the result, the output of the ANOVA. And the ANOVA calculates us the F statistics. F statistics, you know, the theory distributions, you remember probably. We had the F distribution. And as a result of the F distribution, it gives us the p-value, which is here very small. The p-value is less than 0.05. So there is a significant difference between the different categories, education categories concerning the mean height. But there are two more questions. The first question, although we could perform, you should be able to tell me, because we already learned in our previous class that it is possible to compare these individual groups with each other. I could compare using which test? I could compare the primary school and intermediate school, this 130, 163 and 164. Which test I should do if I want to compare two groups, the mean values, mean differences between two groups? Come on.
It's categorical ordinal.
This is numerical data.
Okay.
I have the numerical.
Test?
I want to compare the two groups. I could do
Ampere
the Ampere t-test, of course. I could do the Ampere t-test. So how many Ampere t-tests I have to do? I have to compare this with this with this, none with secondary, none with university, and so on. I have to do all the we call this permutations, the combinations between the different categories, all the possible combinations you have to try. So you would have many hypothesis tests. And remember from our errors in hypothesis tests, the error rate, the alpha error rate, the type 1 error rate would increase very much. Is this clear? What is the disadvantage? Why do we do the ANOVA instead of doing the independent samples t-test, several independent samples t-test? Because the ANOVA gives us only one p-value. Only one p-value. If I would have conducted several independent samples t-test, I would have 10 or more than 10 in p-values, and that would increase, of course, my alpha error. The advantage of ANOVA is it is giving you only one p-value. But still, if you have a significant ANOVA outcome, ANOVA p-value, then you may ask, okay, there is a significant difference between these groups, but which one is different? Is there a significant difference between 155 and 165? Yes, probably, because this is the minimum, this is the maximum. But is there a difference between 163 and 165? Is there a difference between primary school and university concerning the height? This ANOVA is not giving you the answer. If you want to do this, if you want to analyze this, you have to go and do the independent samples t-test. But in the independent samples t-test has the disadvantage of increasing the alpha error. So what is our solution? What is our solution? The solution is to do the post-hoc analysis. I'm just checking whether it is mentioned here in the book. It is not mentioned in the book, probably. Okay. The solution is to do a post-hoc analysis. Let me do it with SPSS. I repeat my ANOVA. First, I have to remove this split file. Okay. Now I want to do it again, the ANOVA. Compare means the ANOVA, one-way ANOVA. As you see, there is an option here, post-hoc and post-hoc comparisons. Under the post-hoc comparisons, we have many options. LSD, Bonferroni, CDAC, Schaeffer. For those with the equivariances assumed and equivariances not assumed. Of course, to do the ANOVA, you need an equivariances assumed. This is one of the assumptions. So you select anyone here. I will select Bonferroni because I will explain you shortly what is Bonferroni. Bonferroni post-hoc analysis and click OK. Let us see the outcome of the Bonferroni. I have again the mean, the descriptives, the homogeneity of variances, the ANOVA result, and plus at the end this multiple comparisons. The no educated ones with primary school, intermediate, secondary, and university compared. The primary school again compared with all the possible, intermediate with all the possible combinations. And here I see the P values for each of them. As you see, the primary school, no educated and primary school, there is a significant difference. No educated, intermediate, there is a significant difference. And there is a significant difference between all other categories and no educated. But the other categories, in between the other categories, there is no significant difference. That's interesting. So that's how we conduct the multiple comparisons without increasing the alpha error rate. How we did this? We did a post-hoc test using the Bonferroni correction. So let me ask you, how many possible combinations are here? How many possible combinations? This is four combinations.
Oh no.
20.
It's not 20. Some of them are repeated, you see. Non and university and non. It is repeated, the same values here. So you have to count them only once. 4, 5, 6, 7, 8, 9, 10. I have 10 combinations. The others are repeated. Right? Do you agree with me?
Yes.
There are 10 possible combinations. So 10 combinations means you have 10 alpha values, 10 alpha values, and 10 alpha values would increase your alpha error to 100%, right? Or not 100%, 50%. If you have one alpha, it's 0.05. All the alphas are 0. Second, also 0.05. And 10 combinations, 10 alpha, 0.05. So you have to add them together. It will be approximately 50%, right?
Yes.
Your error rate, your alpha error was what? The null hypothesis, the reality is there is no difference, but you say there is a difference. You decide that there is a difference. This was alpha error. And this, by this way, it increases fit. What does Bonferroni say? Bonferroni says, if you make multiple comparisons, multiple t-tests, like here, let us do a t-test comparing primary school and intermediate school, okay? Primary and intermediate. I have to do analysis, one-way ANOVA, analysis, independent samples t-test. I just want to compare the height between the two groups, height between the two categories, two categories, category 2 and category 3 I want to compare, okay? Category 2 and 3. Is there a significant difference between these two categories? I have a p-value of 0. Between primary and intermediate, a p-value of 0.435. Let me write this down. This is primary and intermediate. Primary versus intermediate. The p-value was 0.435. 0.435. So this is the p-value. But as you see, primary and intermediate, the p-value is reported after Bonferroni correction as 1. This is the maximum p-value. P-value can be between range from 0 to 1, up to maximum 1. So why it is not 0.4 and 1? Because the Bonferroni correction, multiplies this with the number of tests. Multiplied with 10, which is more than 1 actually. More than 1, but the maximum can be 1. So we report it as 1. Did you understand the Bonferroni correction? Okay. Yeah, this was a bit too much for you, probably. Okay, let me repeat. If you have numerical data, more than two groups, then you go and you do the one-way ANOVA. Okay? One-way ANOVA. The one-way analysis of variance, or ANOVA, gives you one p-value. You have a one p-value, which is telling you that there is no difference between the groups. But after seeing that there is a difference, there is a significant difference, you want to see which group is different between which group. Which differences exist between the groups. So the solution for this is to do individual different t-tests. But if you want to compare all these differences between the groups, you have to conduct 10 different t-tests, and multiple comparisons has the disadvantage of increased alpha error. Okay, therefore we make a correction for correcting the alpha error. One of the possible corrections is Bonferroni. Bonferroni. And what does Bonferroni do? Bonferroni multiplies with the number of tests. Number of tests. So multiplies the p-value. The p-value is multiplied with the number of tests to decrease the alpha error. And instead of reporting 0.4, you report 1.0. Okay. What time is it? Oh, we have to make a break. Okay. The non-parametric alternative of the ANOVA was Kruskal-Wallis test. You probably remember. So if you don't have the assumptions, the normality assumption, or the variances Levene, homogeneity of variances, or your sample size is low, then you conduct the Kruskal-Wallis test. Let me just show you briefly the Kruskal-Wallis test, then we will have the break. Non-parametric tests, legacy dialogues, k-independent samples. Here I have the Kruskal-Wallis test. I have to compare educational levels. And the range is from 1 to 5. I have 5 different educational categories here. And 8. Boy, 8. The only thing with the Kruskal, with the non-parametric test, I want you to remember is it is looking for the ranks. It is not reporting you the mean values. You see, it is reporting you the rank. And of course, you have a p-value, asymptotic significance p-value, and the p-value here is very similar, most of the time very similar to the p-value of the ANOVA. As you see, it is also 0.0 something. Okay, that was ANOVA. Next week I will make you a brief summary, but if you want to be confident in doing understanding the ANOVA is very, very crucial, very important test, hypothesis test in biostatistics. Please read this section, and then next week you may ask me questions so we can discuss it. Let us have a 10 minutes break. Then I will continue with the categorical variables. Data. Categorical variables. Categorical. Categorical outcome. Okay. We had one group, two groups, or more than two groups. Which test we did for the one group?
Sign test.
Thank you. You're great. Yeah. If you don't score 100 at the end of the class, you should object. Okay, I will defend you. Sign test. There are other one group examples, but I will not mention this in this class. One group, sign test is correct. If you have two groups, it can be paired or independent. Paired or related or related. Or independent. If it is paired, we have
McNamara.
McNamara. McNamara's test. If they are independent, or if there are more than two groups, then always we have the chi-square. Yeah. We have the chi-square test. So today we are going to discuss the paired samples. Next week we will discuss the independent samples.
Mr.
Samples. Yes.
Well, we can use feature exact also instead of chi-square.
You're right. You're right. If, next week when we are discussing Fisher chi-square, I will give you also the information about the Fisher exact. You're right. Fisher. You're right. We go for the chi-square, but sometimes the chi-square has sample size requirement, and we cannot meet the sample size requirement. We do the Fisher's exactness. You're right. But today we will discuss the McNamara. What is McNamara? In a McNamara test, you have two related categorical variables, and two categories. In my data set here, I have preference 1 and preference 2. Preference for medication, let's say. Okay, I have asked the preference actually several times, but let's say I asked it twice. Preference means which medication do you prefer? Do you prefer? Sorry, here. Preference 1 and preference 2. These two columns. Do you prefer insulin or do you prefer oral antidiabetics? My scenario is like this. If let me explain you my scenario. I have diabetic patients. And I ask them, which medication do you prefer for controlling your blood glucose? And some patients use oral antidiabetics, some others are using insulin. And you know, sometimes it is better for the patients to switch from oral antidiabetics to insulin, but they are reluctant to do so. So what I did, I gave a course. Had a small patient education class to convince these people to switch from oral antidiabetic to insulin. So my intention was, my expectation was, my hypothesis was that the patients will, those using insulin, oral antidiabetics, sorry, will stop oral antidiabetics and start using insulin. Then after the class, I asked them again, which medication do you prefer now? And you see, these are the responses. At the patient number 1 was using at the beginning insulin. Yeah, preference 1 and preference 2. These are the two columns. Insulin, and he switched to oral antidiabetics. So this was in contrary of what I was expecting. I was expecting that all those using oral antidiabetics, they switched to insulin. This patient didn't change. This also didn't change. Here, one patient was using oral antidiabetic, he switched to insulin. So this was what I was expecting, hoping for, and so on. Is there a significant difference between the patients having preference 1 of changing to another preference? When I have this scenario, I have to do the McNamara's test. Of course, since this is categorical data now, I go for the non-parametric tests and two related samples. I have two related samples. Let me select preference 1 and preference 2 here. Preference 1 and preference 2. And not Wilcoxon, of course, this time, McNamara's test. You see also the other tests here, McNamara's test. That's a very simple outcome here, you see. Insulin, this is after insulin after the education, oral antidiabetic after the education. Insulin before the education, oral antidiabetic before the education. As you can see, 150 people, 51 patients were using insulin before the education, and they didn't change. They continued to use after the education. They continued to use insulin again. 31 patients were using insulin at the beginning. They switched to oral antidiabetics. This was something I didn't expect. I didn't want this. I want this to be zero, but anyways, this is what the patients responded. And 41 patients were using oral antidiabetics at the beginning, before the study, and they switched to insulin, while 207 patients were using oral antidiabetics at the beginning and they didn't change. So as you can imagine, those who make the difference are these two cells, 31 and 41. Do you agree with me? These 151 people, they didn't change their opinion. They used insulin in the beginning, they continue to use insulin. The 207 people here, they also didn't change their opinion. They continue to use oral antidiabetics. But this 31 and this 41 people, they made some change. So the comparison, my comparison, will be based on these two cells, right? Let us see the book. In the book, you see the scenario is given as we observed two pairs of comparisons. Circumstance one, that's, let's say, before the education, and circumstance two, after the education. Before the education, some condition was present or absent, and after the education, it is also present or absent. We have coded them as W, X, Y, and Z. And just look at the formula. The two cells which make the difference are these two cells, right? X and Y. Present in the beginning, absent in the beginning, present later, or present in the beginning, absent in the second attack. So these two cells, X and Y, make the difference. W and Z, they don't have any effect on the change. Therefore, the formula of the McNamara test, by the way, McNamara calculates the chi-square value. It's based on the chi-square distribution. The formula, as you see, is x minus y, the absolute value. These two lines show the absolute value, squared, divided by x plus y. So very simple formula. You don't need to remember the formula, but I want to understand you how simple it is, how simple the logic behind the McNamara's test is. It is very simple. You take the difference between these two and divide them to the sum of these two cells, the sum of these two cells. So in my case, it is 31 minus 41. Here, in my example, the McNamara chi-square would be 31 minus 41, okay? There is a minus 1 here. This is called the continuity correction. But if you have a large sample size, like 30, 40 people, minus 1 would not change much. You agree with me? If you have a low sample size, the minus 1 will be very important in the formula. But if you have 40 people, the minus 1 will not be so important anymore. So this absolute value, minus 1 squared, divided by 31 plus 41. Plus 41. That's the formula. And from this formula, the computer has calculated us a chi-square value of 1.125. 1.125. You remember, as high our test value as significant our result will be. So this is not very high. This chi-square value is 1.1. It is not so high. And the p-value reported here is 0.289. P-value, from that we calculate a p-value, which is 0.289. What is your conclusion when you see this p-value? Is it a significant? Is there a significant difference between the two groups?
No, there's
No.
no significant.
There is no significant difference. So my educational intervention, the conclusion will be, my educational intervention had no effect in changing the opinions of the people to switch from insulin to oral antidiabetics. Although some people, 41 people, switched from insulin to oral antidiabetics, but there are also 31 people who switched from oral antidiabetics to insulin. So it had no effect. It had no effect. The effect is non-significant. There is no significant effect in changing the opinions of the people. Okay, that's it. That's about the McNamara test. All you need to remember is the indication, in which conditions we use it, to related or dependent groups. You must have two related groups, and you have a chi-square. Calculate the chi-square, and the chi-square formula is based, very simple, on the number of people who make a change in their decisions or in their condition. Okay. Yeah. Dr. Azamat, that's enough. That's all I want to say about the McNamara. Can I stop here?
Yeah, I will stop the recording.
Okay.